It's my pleasure to introduce the first talk by Chris Fallin from F5 on partial evaluation. So take it away.
All right, thank you for the introduction. So my name is Chris Fallin, as was just introduced. And this is work that, so I'm currently at F5. This is work that was done while I was at Fastly, and work that was evaluated and written up in collaboration with my co-author, Max Bernstein, who was at the Recurse Center at the time. And so I'll be talking about partial evaluation in order to perform whole program compilation. So first, let's talk about why might we want to use an interpreter-based strategy for dynamic language implementation. So bytecode interpreters are a sweet spot in the design space between simplicity and production-ready performance. By this I mean that they're a significantly less effort to implement than a full just-in-time compiler with type inference and all the rest, but they actually provide reasonable performance that could be used in production. And so for this reason, many dynamic language implementations use just an interpreter-based strategy for a significant portion of their lifecycle. Also, interpreters are very portable. That's relevant. So to give some context for this project, about 4 years ago, I ported SpiderMonkey, Firefox's JavaScript engine, to run inside a WASM module. That is on top of a WASM-based platform. And this was used for a function-as-a-service platform. It was kind of a plugin or a request handler. Because SpiderMonkey has an interpreter tier, excuse me, this was actually quite straightforward. So interpreters work, but they're a little bit slow. And so when one wants more performance, one might start to consider adding a compiler to native code. So typically in a just-in-time or dynamic language implementation, one would add several tiers. The first tier one would consider is typically called a baseline compiler. The idea here is that one has implementations for each bytecode. One simply splats those implementations one after the other, generates the code, so very simple, very fast. And then when one needs more performance, one begins to think about building an optimizing compiler tier. The way this will work, at least for a dynamic language, is that one wants to build type-specialized code. And so one does a type profiling pass, or profiles types as the code runs in lower tiers, and then combines these types with the individual implementations of bytecodes to produce one wholly optimized function body. Unfortunately, in the port of SpiderMonkey to WebAssembly that I mentioned, these tiers are not available simply because it's a new ISA, a new platform, and there was no implementation to generate WASM bytecode. Moreover, on this particular platform, it was quite interesting. JIT is fundamentally not possible. So for both security and for operational and management reasons, it was not possible to add new code to the system at runtime, right? And so the whole modality in which this JIT-based platform worked would not be possible to build on this platform. Instead, what we would need to build if we wanted more performance than the interpreter would be a full ahead-of-time compiler backend that's completely separate from the existing JIT infrastructure. Right? So building this is an enormous engineering effort, both initially and to maintain sort of in perpetuity. And so we asked ourselves the question, right? There's an opportunity to ask, is there a better way to build this? So let's consider what one does when one builds an interpreter and compiler tiers for a language implementation. When you write the interpreter, you write the semantics for every bytecode directly, and those semantics execute when the opcodes are reached. When you write the baseline compiler, you write code to emit the instructions implementing the semantics. Those instructions are emitted and then executed. When you write an optimizing compiler, you write code to emit the IR nodes implementing the semantics of each opcode, and those are optimized together, emitted, and executed. So these are three different encodings of the semantics for the bytecode. This can lead to all sorts of issues, subtle incorrectness errors as they mismatch. It's also, as I mentioned, a significant increase in the engineering effort, including ongoing as we add new features to the language. So the ideal would be that we generate the compiler from the interpreter. And right, all these different semantics are fundamentally expressing the same thing, just in different ways. So why not take the direct expression of those semantics in the interpreter and automatically derive the compiler tiers? This would give us a single source of truth. It would reduce engineering effort, both initially and as we maintain the thing over the long term. And it would eliminate mismatches by construction. So this idea has been around for a while, in fact, 54 years, I think. It's called the Futamura projection, at least when you do it via partial evaluation. It's called the Futamura projection. And the idea is that we partially evaluate an interpreter with the program that it's interpreting to perform a compilation, right? So the residual, the piece that can't be evaluated away, is a compiled form of the bytecode that was interpreted. So there are several items of past work that have made this practical. One of the most well-known probably is the truffle system, which is built on top of GraalVM, which is a Java runtime. This was published in our very own PLDI 8 years ago. The way it works is by taking a constant snapshot of an AST, an abstract syntax tree, and an interpreter for the AST, and inlining, and so constant propagating the AST into the interpreter, inlining the handlers for every node on the AST up to some boundary, and then that produces effectively compiled code. This works quite well when it works. Unfortunately, it requires rewriting the entire language runtime into this framework, right? So it wasn't really applicable to our use case where we had a large existing runtime. We wanted to stay close to upstream. We wanted to minimize maintenance cost. Also, as far as we know, it only works at runtime. It's unclear if ahead-of-time operation is possible. One of the other main approaches here is meta-tracing, or tracing in general. A good exemplar of this approach is the PyPy implementation of Python, which is built on RPython. And the way this works is that you have an interpreter over bytecode. You trace the execution of that interpreter over the bytecode, and you record the actions it performs. That's the trace. And then you compile that trace to machine code. And so this also works quite well when it works. It can see through a lot of abstractions. It's quite fast. Unfortunately, it requires rewriting the interpreter into the framework, just like Truffle. Also, it, even more fundamentally than Truffle, can only operate at runtime because it requires observing the execution of the interpreter in order to produce the trace. So our goal in this work is to build a solution that's fit for our needs, a practical full method ahead-of-time partial evaluation engine for existing bytecode interpreters, such as SpiderMonkey written in C or C++. And our contribution in this work is a tool that we call Weevil, or the WebAssembly Partial Evaluator, that does just that, as well as an adaptation of SpiderMonkey, the production JavaScript engine, for its interpreter tier to be partially evaluated into a compiled WASM code. So let's dive into how this might work. Let's take a very simple interpreter. This interpreter only runs one opcode. And let's see how we might apply standard compiler techniques to partially evaluate. So let's apply constant propagation. Let's say that we know that the byte at *PC, the opcode, is the constant add. So we can go ahead and plug that into the program, do the substitution, and then we can do branch folding. We know the target of the switch because the selector for the switch is a constant. And so we take just the body for the add opcode implementation. And so this looks like a compiled form of the add opcode, right? So great, partial evaluation works. All right, let's go back to that interpreter. Let's make it a little more interesting. Let's wrap the switch with a loop. So this is now an interpreter for multiple opcodes. And let's give it a program of two opcodes, add and return. So here's the control flow graph, or CFG, for that interpreter. There's the entry, there's the loop header, and then there's a switch over many possible opcode implementations, and then a back edge to execute the next opcode. So let's do our constant value analysis. We start with the known state PC equals 0. We can go ahead and do branch folding as before. We increment PC. We know PC equals 1 on the back edge. That flows back into the loop header. And now, as is typical for data flow analysis, we need to meet all of the in edges into that block. And so in the constant value lattice, constant 0, constant 1 meet to bottom, which means not constant, right? And this is actually accurate. This is true. In fact, we know here that PC is not constant. Stated plainly, PC changes every iteration. So we see that if we just take constant propagation and branch folding as our basis for partial evaluation, this is not going to work for any practical bytecode interpreter. So the first key idea in this work, one of the key ideas of Weevil, is that we use context sensitivity. So the idea here is that we evaluate each iteration of the interpreter loop in a separate context. And I'll tell you where these contexts come from in a moment. But by doing so, we keep the states from meeting. We keep the constant propagation from collapsing. So here we have essentially a separate analysis context in which we're seeing another view of the same interpreter loop. You can think of it as unrolling the loop and making a copy for every opcode, although we don't actually do that in practice. And so PC equal 1 flows into the next context. We know a constant PC for every static program point in this context-sensitive view. We can then do branch folding. And we have essentially the equivalent of a template compiler. We get the implementation for each opcode, and they're glued together in the program flow. So where does this context come from? Well, in Weevil, we require annotations in the interpreter, minor annotations. And the idea is that the interpreter author annotates where the context changes. So in this example, it's PC. It could actually be anything. Weevil is a general tool. But the idea is that as we do the constant value abstract interpretation and process each block, we can follow these intrinsics, and we can update the context as flow-sensitive state. And this allows us basically to drive the traversal dynamically through all the possible PC values. One really important thing to note here is that these are not load-bearing for correctness. So you could get these wrong, and the worst that would happen is the analysis collapses back to the runtime state, the not specialized state that we saw before. They're only to make the analysis work. So here's a more detailed example of the Weevil transform. Here we have a control flow graph again with the header, the opcode implementations, and the footer. The way the transform works is we take the interpreter CFG, we call it the generic function. We're specializing it for some constant input. And so we'll produce a specialized version of this function for that bytecode on the right. We do this with several memoization maps. So we memoize the context-sensitive block and value, SSA value ID to blocks and values on the right-hand side. And we'll see why that's important in a moment. This whole thing is work queue driven. So we basically just lazily follow all reachable code with this work queue algorithm. So for each block that we pop off the work queue, we partially evaluate that block with constant propagation. We track the context as part of the flow-sensitive state, as I mentioned. And then when we reach branches, we enqueue the branch targets on the work queue with the current that is maybe updated by intrinsics context. So I'll give an example here. We'll start with PC equals 0. That's our initial state. We go ahead and take the initial block. That's the entry to the function. And we'll specialize it based on the known opcode at that PC. We'll copy over the blocks for that opcode. We have an update context intrinsic. So when we see the out edge from block 6 back to block 1, we need to process block 1 in context 1 rather than 0. So we'll copy it over again. We'll copy the opcode implementation and constant propagate it for the next opcode. Let's say that the program that we're specializing on is a two opcode program, add and then go to 0. So an infinite loop around the add opcode. The really interesting thing here is that because we memoize the specialized blocks, when we process the branch target out of block 6, the back edge here for the PC equal 1 context, we actually look up and find the original block from context 0. So this is really important. What this means is that the bytecode control flow graph is preserved, right? This is not a trace compilation. This is not following some linear path through the bytecode and producing a linear stream of specialized code. This actually, lazily via the work queue algorithm, finds all reachable code and reproduces that control flow graph of the bytecode exactly in the compiled code. So this is a whole function compiler. There are more details in the algorithm that I won't, more details in the paper that I won't go through, details of how the algorithm works, how it interacts with SSA, et cetera. The last thing I want to tell you about is how we applied this to SpiderMonkey. So SpiderMonkey, as I mentioned, is Firefox JavaScript engine. It runs, as we ported it, it runs inside of a WASM module. And this is useful for function as a service and other plugin scenarios. And Weevil was specifically developed, at least initially, to do the AOT compilation for this engine. The way this works is sort of with a snapshot methodology. So we start with spidermonkey.wasm. That's the interpreter compiled to a WASM module. We load the JavaScript source into it, and then we snapshot the state of the WASM heap, and we dump that as a new WASM module. So it's a WASM module with an initial memory state that contains bytecode objects. Weevil then processes the snapshot, takes the interpreter, and partially evaluates it over that bytecode, appending new WASM functions to the WASM module. So that's all well and good. That gives us a compilation of the JavaScript bytecode. But one finally might ask, how is AOT compilation of a dynamic language possible, given what I said earlier about type profiling and the need for JIT? So the last thing I'll tell you about is that in the JIT compiler world, typically the baseline compiler layer actually doesn't depend on types. And so the way this works instead is that the bytecode is more or less one-to-one with the semantics of the source language. So there are polymorphic opcodes like add and equality check. And the interpreter uses something called, or the baseline compiler uses something called ICs, or inline caches, which are little type-specific stubs of code that are added at runtime for the actual type cases that are seen. And these are reached via pointers that can be updated at runtime. So they can be plugged in without actually changing the code. However, typically, in a native scenario, the JIT compiler will dynamically generate these IC stubs themselves. So it does require JIT compilation at runtime just to generate these little bits of code. So the key idea, at least with the IC sites here, is that the late binding of the execution semantics, so dynamic types tell us what to do only when we reach that program point, becomes late binding in the compilation strategy, right? We just have an indirect function pointer that we can update at runtime. However, as I mentioned, we need, at least in the current scenario, the JIT compiler to generate these stubs. And so what we realized was we could actually make this ahead of time by collecting all of the possible ICs ahead of time and compiling those before we ever run the code. So concretely what we do is we run SpiderMonkey's unit test suite, collect all of the ICs that it generates. This is nice for sort of social project organization reasons because you'll write a unit test if you add new functionality. So we collect this corpus, and then we Weevil this, we partially evaluate it alongside the JavaScript functions, and we simply have a lookup table to find these at runtime. So we can actually run all in specialized code with no JIT compilation. This is fully ahead of time compiled in all of our benchmarks. So I'll tell you about our benchmarks. Very briefly, we have the Octane suite, which is a standard suite for JavaScript engines. We evaluate it here with a generic interpreter with ICs, and then our tool applied in several steps. The speedup that we see over the interpreter with ICs, which we can take as a fair baseline, is 2.17x. If we take the generic interpreter without ICs, which was actually the state of the world before we started this entire project, 2.53x up to 4x. So this is quite a significant speed up. There's some remaining performance to be had because calls are a little slower on WASM than they are on native. So ICs are still slower than they could be, but this is quite good. And it is actually in production. So customers are using this today. There's a flag on the runtime built around SpiderMonkey that can be used to enable this. And so it's seen real use cases, it's stable, and it's providing real speedups. Finally, in the paper, we do talk about some results on a Lua interpreter and a Toy interpreter as well to show this is general and not specific just to the way that SpiderMonkey works. Thanks, and I'll now take questions.
If you have questions, please step up to there. Good. Step up to the mic.
For the stream, 1 second. Wait for them to.
Okay. Emergency. Does that work? Yes. Okay. Thanks. Right. Thanks for the great talk. First of all, I was wondering. So, in your analysis, when you have a loop, you kind of each different iteration of the loop is a different analysis context. I think. Like obviously, like if there's a while true loop that. Like at some point you have to merge back, right? What's the heuristic to make that merge, and how does that work?
Yeah, so the thing I didn't mention in too much detail is that it looks like a standard data flow analysis with a fixed point algorithm. So we update the state into a given block in a given context when we see a new edge. If the incoming abstract state does not change, then we don't reprocess, and so we'll reach a fixed point just as a normal analysis would reach a fixed point.
All right, thanks.
Yeah.
Hi. Leonard from University of Montreal. Thanks for the great talk. I have some knowledge about basic block versioning, and it looks like this is kind of similar analysis. And one thing I know about basic block versioning is that it's hard to keep the context between function calls. So I'm wondering, how do you treat this case?
Yeah, that's a great question. So first of all, it is very much like basic block versioning. You can think of it as kind of orthogonal in the sense that we are specializing on PC as the context. BBV does type context, right? So they could actually be combined if you want. That's interesting future work. As far as interprocedural goes, we don't actually specialize across functions, so it's a very simple answer. So that is one requirement on the shape of the interpreter, that all of the pieces that need to be specialized or splat out per opcode exist in a single function at the WASM level. One could imagine doing some sort of interprocedural specialization where you say, I want a function pointer just for this other function I call in this context. Yeah, we haven't done that yet, but that would be interesting.
Thank you.
Hello, yes, check. Hi, Ralph Jung from ETH Zurich. So thanks for the talk. I was wondering, you mentioned you are using the test suite to gather these little snippets of like the actual implementations for all the operations. Does that mean there's some risk here that you're going to end up missing some?
Yeah, it could happen in theory. And so, in fact, so I glossed over, I said all possible ICs. There are some cases where ICs are dynamically generated based on, for example, the length of a JavaScript prototype chain, right? So if we don't have it, what happens is the cache IR, which is the IR for the IC, will still be generated. It will be interpreted by the cache IR interpreter during runtime, which is still faster than not having the IC at all. Yeah.
Thanks.
Go ahead. Last question.
Hi, Sungwon from NYU. I actually had the opposite question where, if I'm understanding things correctly, compared to something like a tracing interpreter, you have a chance of over-approximating, where you generate some code for a path that actually doesn't really get run for your specific application. So how much is the code? How much difference does there exist between the code size from like a tracing versus your system?
That's a really interesting question. So it turns out to bloat quite a lot, actually. So in our particular use case, that didn't matter much. We were compiling, we were memory mapping the code in. So if it's cold and never used, then that's fine. It does actually matter in a lot of cases. You want small code results. So one thing that could be done is the Weevil specializations are optional in the sense that the way the tool works is that it will do the specialization, then stick a function pointer somewhere to say, OK, it now exists. You could add some metadata to the compilation result to say, if it's not actually called, you can delete it as long as you null out this function pointer. And so you could do that and then have a runtime profiling pass, or as your system runs it, it could say, I actually have memory pressure, I need to shrink the code, and I can delete the things that weren't actually run. So that's interesting future work. Yeah.
All right. Thank you. Let's select Chris again.